Take a high-level look into recurrent neural networks. Sequential data refers to data that is collected over time or has a specific order or sequence to it. This type of data can be found in many different forms, including speech, text streams, audio clips, video clips, and time series data. The key characteristic of sequential data is that each data point is dependent on the previous data point in the sequence. Sequence models are a type of machine learning model used for processing and analyzing sequential data. Sequence models are designed to take into account the dependencies between data points in a sequence. They can be trained to predict the next value in a sequence, generate new sequences, or classify sequences based on their content. The key point for sequence models is that the data we are processing are not anymore independently and identically distributed samples, and the data carry some dependency due to the sequential order of the data. Sequence models are very popular for speech recognition, voice recognition, time series prediction, and natural language processing. Recurrent neural networks are a type of sequence model and are particularly well suited for processing sequential data. Recurrent neural networks are a powerful and robust type of neural network and belong to the most promising algorithms in use because it is the only one with internal memory. Because of their internal memory, recurrent neural networks can remember important things about the input they received, which allows them to be very precise in predicting what's coming next. This is why they're the preferred algorithm for sequential data. Recurrent neural networks can form a much deeper understanding of a sequence and its context compared to other algorithms. To understand recurrent neural networks properly, you'll need a working mechanism of feed-forward neural networks. In a feed-forward neural network, the information only moves in one direction from the input layer, through the hidden layers, to the output layer. This is because the feed-forward neural networks are only meant for data points that are independent of each other. Feed-forward neural networks have no memory of the input they receive and are bad at predicting what's coming next. Because a feed-forward network only considers the current input, it has no notion of order and time. It simply can't remember anything about what happened in the past except its training. However, if we have data in a sequence such that one data point depends upon the previous data point, we need to modify the neural network to incorporate the dependencies between these data points. In a recurrent neural network, the information cycles through a loop. When it makes a decision, it considers the current input and also what it has learned from the inputs it received previously. Simply put, recurrent neural networks add the immediate past to the present. Therefore, a recurrent neural network has two inputs, the present and the recent past. This is important because the sequence of data contains crucial information about what is coming next, which is why recurrent neural networks can do things that feed-forward neural networks can't. Recurrent neural network cells distinguish themselves from the regular neurons because they have a state, and thus can recollect details from the past. RNN cells form the spine of recurrent networks. A sequence of inputs is passed through an RNN cell, one at a time on a mathematical level. The state of the cell assists it to remember the past series and combine that details with the current input to provide an output. An easier way to view it is by unrolling what happens during the sequence, revealing a simpler deep network. The RNN cell consists of input xt is taken as the input to the network at time step t. For example, x1 could be a one-hot vector corresponding to a word of a sentence. Hidden state, ht represents a hidden state at time t and acts as the memory of the network. It is calculated based on a weighted combination of the current input and the hidden state at the previous time step. The function f is taken to be a nonlinear transformation. A typical recurrent neural network relies on past and present events. However, there can be situations where a prediction depends on past, present, and future events. For example, predicting a word to be included in a sentence might require us to look into the future, i.e., a word in a sentence could depend on a future event. Such linguistic dependencies are customary in several text prediction tasks. Thus, capturing and analyzing both past and future events is helpful. To enable straight and reverse traversal of input, bidirectional RNNs or BRNNs are used. A BRNN is a combination of two recurrent neural networks. One recurrent neural network moves forward, beginning from the start of the data sequence, and the other moves backward, beginning from the end of the data sequence. The outputs of the two recurrent neural networks are usually concatenated at each time step, though there are other options, like summation. Backpropagation through time, or BPTT, is the application of the backpropagation training algorithm to recurrent neural networks applied to sequence data. To understand the concept of backpropagation through time, you'll need to understand the concepts of forward and backpropagation first. We could spend an entire video discussing these concepts, so I will attempt to provide as simple a definition as possible. In neural networks, you basically do forward propagation to get the output of your model and check if this output is correct or incorrect to get the error. Backpropagation is nothing but going back through your neural network to find the partial derivatives of the error with respect to the weights, which enables you to subtract this value from the weight. Those derivatives are then used by gradient descent, an algorithm that can iteratively minimize a given function. Then it adjusts the weights up or down, depending on which decreases the error. That is exactly how a neural network learns during the training process. So, with backpropagation, you basically try to tweak the weights of your model while training. BPTT is basically just a fancy buzzword for doing backpropagation on an unrolled recurrent neural network. Unrolling is a visualization and conceptual tool, which helps you understand what's going on within the network. Most of the time when implementing a recurrent neural network in common programming frameworks, backpropagation is automatically taken care of, but you need to understand how it works to troubleshoot problems that may arise during the development process. You can view a recurrent neural network as a sequence of neural networks that you train one after another with backpropagation. Now the questions that should come to your mind are: what is the total loss for this network? How do we update the weights and bias values? In order to do backpropagation through time to train a recurrent neural network, we need to compute the loss function first. The total loss is simply the sum of the losses over all timestamps. Note that the hidden to output weight is shared across all the time sequences. Therefore, we can differentiate it at each time step and sum it all together. Now, let's go through the details to derive the gradient with respect to hidden weight. From the equations of the forward pass, we know that the hidden state at time step t+1 is dependent on the hidden state at time step t. With that in mind, the gradient is calculated using the chain rule for multivariable function. Finally, BPTT work on deriving the gradient with respect to input weights. There are four main types of RNN. One-to-one recurrent neural network, one-to-many recurrent neural networks, many-to-one recurrent neural networks, many-to-many recurrent neural networks. One-to-one with a single input and a single output. It deals with a fixed size of the input to the fixed size of output, where they are independent of previous outputs such as image classification. One-to-many with a single input and multiple outputs. It deals with a fixed size of information as input that gives a sequence of data as output, such as image captioning takes the image as input and outputs a sentence of words. Many-to-one with multiple inputs and a single output. It takes a sequence of information as input and outputs a fixed size of the output, such as sentiment analysis, where any sentence is classified as expressing the positive or negative sentiment. Many-to-many with many inputs and many outputs. It takes a sequence of information as input and processes the recurrently outputs as a sequence of data, such as machine translation, where the RNN reads any sentence in English and then outputs the sentence in French. Now take a look on implementation code.